Hello, this is Team 11. In this video, our team will be presenting on our project on model predictive control design for multiple aircraft landing guidance. My name is Cage, and I will be presenting along with my team members, Chenlin, Xinglong, and Tingyu. So first, I will give a brief introduction on our topic and also our motivation for solving such problem. In response to the increasing volume of air traffic in recent years, the FAA is developing a next-generation air transportation system that can make flying safer, more efficient, and more predictable. As we know, the current air traffic management is a centralized process. A human ground controller will send out commands to pilots that tells them where to go. The ultimate goal of the next generation system is to decentralize the system and eventually reach the free flight condition, in which the pilots can take full control of their action. However, because of the complexity of the decentralized system, our goal for this project is to design a centralized MPC algorithm to provide autonomous landing guidance for aircrafts. And next, Tingyu will talk about our problem formulation.
Considering the complexity of the system, here we're gonna make some assumptions to simplify our problem. First, we assumed all aircraft are approaching to the land and a single runway Class D airport. Second, we only consider 2D plane motions of the aircraft. Third, we assumed aircraft are in a steady level flight condition. As shown in the figure on the right-hand side, there are 3 planes that we chose to simulate, including Cessna 172, Cirrus Vision Jet, Boeing 747-200, and we only consider 2 degrees of freedom of the aircraft, its position with respect to their inertial frame. From the figure, the initial position of each aircraft will be generated randomly in an area of 10 kilometers away from the airport. As all of the aircraft intend to be land and airport, an MPC will be designed to control the trajectory by using speed and handing angle as a control inputs. We created the dynamics models for our aircraft. Their formulas on the left-hand side. XYZ represent Cartesian coordinate for aircraft. UV omega represent speed of aircraft corresponding to XYZ axis. PQR are the angular velocity of the aircraft corresponding to the XYZ axis. And theta, psi, phi represent path angle, handing angle, bank angle separately. For simulation, we simplify the problem from 3D to 2D. So we set theta, phi, omega, r be 0. Now we got new dynamics equation set, as shown on the right-hand side.
The general logic of our design is as follows. We start with initializing aircraft positions, which in this case is randomly generated. While the aircraft has not reached the target runway, the aircraft will first try to land based on forward set with guiding reference. Then we generate the inputs such as aircraft speed and time step using the MPC that we design, and then use the optimal inputs to update the aircraft's control. The whole process then rinse and repeat until the aircraft reaches target runway. The model and the input constraints are shown in the slides. Essentially, we're setting the heading angle to be between negative pi over 4 and positive pi over 4, and we have speed constraints for aircraft speed in both x and y directions. And here are some of the results that we have ran. The figure on the left shows the result when we set n equals to 4, and the figure on the right shows the results when we set n equals to 20. Judging from the 2 figures, the simulated aircrafts were able to start heading to the runway from their initial position. The MPC seems to be working as intended. However, the performance is not stable at the moment. There are runs that we have simulated where the aircraft would start to head away from the runway, but we were not able to identify the cause of the problem. In addition, what we could have done is to add in a feature where we can remove aircrafts from simulations if the aircraft has arrived at the runway, which is the green inner circle. This feature would not only help with the runtime of the program, it would also help make the graphs a lot more clear and have a chance to prevent errors. Another feature we could add is collision prevention. As shown in the graphs, two of the aircrafts, the green one and the red one, would collide with each other if they start from their initial point at the same time. However, adding collision prevention would introduce other variables which would take a lot more time to do. We might work on these new features in the future.
To conclude our presentation, we successfully incorporate the MPC design to simulate a few aircrafts landing at a target runway, and we could compare the different performances by modifying some parameters such as the input constraints and the prediction horizon. But as we mentioned, our MPC design is not recursively feasible, as for some tests, the aircraft doesn't want to stop after reaching the runway. So based on these, we can make some future improvements, such as model the system as a 3D space for more accuracy, and develop a collision avoidance algorithm within the airspace for both landing and takeoff. So lastly, we can also test out our algorithm by adding more aircrafts to the simulation. That's it for our presentation. Thank you for listening.